How's it going, everyone? I'm trying out something new today. Doesn't really affect any of us, but I do have my tablet here. With the chat, I can try to put it right in front of me. That way I'm not turned to my side. Could be interesting. Maybe not. We'll see how it goes. I don't know how much it's going to drain the battery either, because it's not plugged in right now. But, anyway, I'm trying that out. I'll see where the battery is after this class, and go from there. Anyway, hope you all are doing all right. Last time we started with section 5. Were there any questions there before we continue? Oh yeah, we're moving right through it. Okay, no questions on homework or anything? Okay. Alright, so last time we talked about synthetic division and the factor theorem and how to use that to test whether a binomial is a factor of a polynomial. And we also looked at the potential rational zeros theorem that lets us know what the possible solutions are to a polynomial. So let's start looking at some examples of how we would actually utilize this. And that's what we'll do today with section 5 or section 6 and section 7. But let's look at 46 first. We have f of x is x squared plus 8x squared, or sorry, x cubed plus 8x squared plus 11x minus 20. Alright, now we want to start off with our rational zeros theorem, or possible zeros, sorry. So p is equal to 20 in this case, q is 1, so again, p is the constant here, and q is the coefficient in the lead term. And again, it doesn't matter if it's plus or minus, because we know all the options are positive and negative anyway. The factors of 20 are 1, 2, 4, 5, 10, and 20. And the factors of 1 are just 1. That's 1 times 20, 2 times 10, and 4 times 5. Okay. And so P over Q is plus or minus 1 over 1, 2 over 1, 4 over 1, 5 over 1, 10 over 1, and 20 over 1. So it's just the same 6 numbers we got for the factors of 20. However, they could be plus or minus, so technically that's 10 possible solutions that we have. Now, what we do here, once we establish what our rational zeros are, or potential zeros, we go ahead and plug them in using synthetic division. Now, what I usually do is I start from the lowest whole number values and work my way up. So I would suggest doing the same, starting with 1, and if 1 doesn't work, then -1, 2, then -2, 4, then -4, and so on until we get to one that works. Most of the time we should be able to do that pretty quickly. It's very unlikely it's going to be these higher, like 2-digit numbers. But in an equation like this, it could be as high as 5 as one of our factors, or one of our zeros. And so the nice thing is that we only have to find one that works. And usually it's one of the smaller numbers versus the larger ones. But so I would say let's start with 1, and then -1, and then go from there. So we try x equals 1. That means in our box here, we'll go ahead and put 1. Our coefficients of the polynomial, 1, 8, 11, and -20. Following that, we go through the process of synthetic division. We bring the first number down, we multiply, add, multiply, add, multiply, add. Does this mean that x equals 1 is a 0 of the polynomial? Yes. Yeah, we got a remainder of 0, so yes, it is. So, specifically, what does this tell us? A remainder of 0 tells us 1, x equals 1 is a solution, or is a 0. 2, x minus 1 is a factor. Okay. Now notice that x is equal to 1 here, but then we have x minus 1 here. Remember that going from a binomial to a value, we always look at the solution of that binomial. So x equals 1 is the solution of x minus 1 when it's set equal to 0. So whatever number is here is being subtracted here. This is sometimes a little bit confusing. But not only does it tell us that x minus 1 is a factor, it tells us the other factor is based on what's next to our zeros right here, or 0. Which is a 1, a 9, and 20. Those are the coefficients of the other factor now. And so we can rewrite f of x. We know x minus 1 is one factor thanks to this result. What is the other factor? X squared plus 9x plus 20. We have 1x squared, a 9x, and a 20. And again, we know this one is x squared because it starts one less than the original polynomial, which was x cubed. Essentially, we took out an x, so now it's x squared. Alright, and from here, once we get it down to where it's a quadratic trinomial, we can continue to solve this any way that we choose. We don't have to keep going with synthetic division. We can just continue by factoring x squared plus 9x plus 20. And so here we need two terms that multiply to 20 and add to 9. What would that be? 4 and 5, good. So we get f of x is x minus 1, x plus 4, and x plus 5. And that completely factors our polynomial. So we've taken a cubic polynomial and factored it into 3 binomials. It's a little bit more convoluted process, and there's a little bit more trial and error here than what we did with the quadratics. But the outcome is still the same. We have the same goal of just breaking down the original polynomial as far as we can. And so we end up with x equals 1, x equals negative 4, and x equals 5 as our three zeros. So if instead of 1 we had tried negative 4 or negative 5, then those would have worked as well if we chose to use synthetic division. So it does give us a little bit more that we can work with as far as things that we can factor, which is important. Anyway. Let's do some more of these, of course. Let's see. Now the book will actually include some problems where it's x to the 4th is where we start out, rather than just x cubed. And we'll look over one or two of those, but on the test I'll probably just stick to x cubed. That way it's complex enough we can demonstrate our knowledge of the topic without just going overboard completely. I would like to do some with x to the 4th. Let's see. So let's try 50. With a 54, that might be interesting. I'm going to try to rotate this. Hopefully the image turns. No, it's not going to turn. It's going to be inconvenient because I might have to have it plugged in while I use it. So that's just the thought. So, I don't have a stand for it that would allow me to plug it in. Anyway. It's also very bright. I've got the brightness way up. That should help. Okay. So I said 50, 52, no, 54 is what I said. Okay. F of x is x to the fourth. Let's see, minus x cubed minus 6x squared plus 4x plus 8. Now, when we start off with x to the fourth, we know that once we find one of our zeros, that'll get it down to x cubed, which means we'll have to keep going and test out more solutions. There is a bit of logic that we can use here to help us simplify this process, but other than that, it can be a little tedious at some points. Okay, so P is 8, Q is 1, our factors of 1 is just 1, and for 8 we have 1, 2, 4, and 8. And so those are the potential rational zeros, 1, 2, 4, and 8, positive or negative. And so that's what we'll try. So let's try x equals 1 first, because that's always nice when that one works. I knew it would work for the last one. I don't know about this one. I'm thinking no, but we'll see how it goes. Okay, so it means we put 1 here, and across here we have the coefficients of our polynomial. I don't know why I put a plus there, but I did. Anyway, so we bring down the first one, and then multiply, add, multiply, add, multiply, add, multiply, and add. Now, the number in this last box is our remainder. If our remainder is 6, what does that tell us about this x equals 1? It's not a 0, right? So x equals 1 is not a 0. Okay, that means we have to try something else. So let's try x equals negative 1. And if that doesn't work, then we'll go to 2 and negative 2, and hopefully by then we'll get something to work. -1, -6, 4, 8. Oh, that was good. Yeah, that one worked out. Okay, so we got a remainder of 0. That means x equals 1 is the solution, or it is a 0. And what would the factor be that goes with x equals -1? What does that correspond to? X plus 1. Alright. Now, not only do we know x plus 1 is a factor now, then we have x cubed minus 2x squared minus 4x plus 8 as our other factor. Now, because we're still not to a point where we can just factor this ourselves, what we can do is just keep going with synthetic division, but we'll use this new polynomial rather than the old one. That'll make it a little bit easier as a result. So we'll use just these 4 terms rather than the original 5 when we set up our synthetic division. So now we already know that we've broken down the original polynomial to these 2 factors. Now we just have to factor this. We don't want to worry about that. So we still have these 4 terms. Our p over q is actually still the same because p is still 8 and q is still 1, so we'll use the same numbers. Well, one thing I'll add, and this is where the logic kind of comes into this, is that we already discovered that x equals 1 didn't work. Now, if it didn't work for our original polynomial, that means it's not going to work for this polynomial. Okay? Unfortunately, x equals 1 is the only one that we can roll out. It may happen that x equals negative 1 is a 0 a second time. That's why we want to make sure we use these new coefficients, because we already know x equals negative 1 works for the original polynomial and gave us a 0. If it also works for this polynomial and gives us a 0, that means it's a solution a second time. We don't know for sure until we try that, though. So I always recommend whichever one we just found on these x to the 4th problems, go ahead and try it again with the new coefficients. So we have 1, negative 2, negative 4, 8. Now, it may not work, but we'll just go through it. Bring down 1, negative 1, 3, multiply is 3, and negative 1, 1, 9, no. So we get a remainder of 9, and clearly that's not 0, so it's not a 0. So x equals negative 1 was a 0 once, but it's not a 0 a second time. But that's one thing we do want to check, because it is going to be a lot easier to check negative 1 than it will be to check a larger number as far as going through the synthetic division. Okay. So, I'm out of paper, so I have to flip this over. And this is where, like I said, it does sometimes take a little bit longer, especially on these x to the 4th problems, because there are 4 different solutions that we have to find. 2 of them by synthetic division and the other 2 by factoring, most likely. And so where we're at, we've already said f of x is x plus 1 times x cubed. Let me make sure I copy this over correctly. Minus minus plus minus 2x squared minus 4x plus 8. Okay. And we already tried 1 and negative 1. We've ruled those out. So we move forward with 2. 1, multiply, because it's 2, add, 0, multiply, 2, add, negative 2, multiply, negative 4, add, 4. So no good with 2. X equals 2 does not work. So we try x equals negative 2. Negative 2, negative 4. This would be 8. 4. Negative 2 times 4 is negative 8. Add these, you get 0. And there we go. Uh-oh. So does anyone else see the mistake I made? That's a pretty serious one. Right here, yeah, 2 times 0 is not 2. In fact, we got negative 2 to work. Looking at this numbers down here, that means x equals 2 is going to be a solution twice. Yeah, so this should be a 0. This should be negative 4. This should be negative 8. And this should be 0. And x equals 2 should work. That's why I don't want to go too quickly. I was trying to go too quickly on that. So we could actually go either way. Now that we found 2 of the remaining 3 solutions. The only problem is we can't say x plus 1 times x minus 2 times x and plus 2. Right, both of them do work. Yeah. We can only use one of those because then we have to use the other part to solve for the other 2 solutions. So let's pretend I didn't mess up x equals 2. We know x equals negative 2 is going to be one of the remaining solutions, but we would get f of x is x plus 1. X equals 2 does work, so x minus 2 is a factor. X minus 2. And the other factor here would be x squared, 0x minus 4. So x squared minus 4. And so the question is, where do we factor from there? Well, we absolutely know one of the factors is x plus 2, since we just got x equals negative 2 to work also. So that means we need 2 numbers that multiply to negative 4 and add to 0. Negative 2 and positive 2. Good. So we have x plus 2 and x minus 2. And now it's completely factored. Okay. So we were able to factor that completely. But like I said, I'll just give you one or two of these to look at on homework. But when it comes time for the test, I'm not going to give you these fourth degree polynomials. I'll just stick with the third degree polynomials because I feel like those are sufficient enough for us to demonstrate our ability without spending a lot of extra time doing those problems. So these do take a little bit longer to go through the fourth problems because of the second synthetic solution that we need to find in order to break it down to where we just have a quadratic term to factor at the end. Let me present this problem to you in a slightly different way. Let's see. Given f of x equals x cubed minus x squared minus 14x plus 24, if one factor is, let's say one factor is x plus 4, what are the remaining factors? A could be x plus 2, x plus 3, b, x minus 2, x minus 3, c, x plus 1, x minus 5, or let me say 6, that'll be slightly more believable for a wrong answer. And then x minus 1, x plus 6. Okay. So basically I wanted to present this to you as one of the ways I like to ask the question on the test is go ahead and give you one factor and see if you can find the remaining factors. That means, one, we have to go through synthetic division, but we know which number to try first based on this. And then can we get the other two factors from there? It's one way I can kind of shorten the test as far as how much time we need to take, but also ask questions that are testing exactly what we want to test over. Okay. So we know one factor is x plus 4. We can go and set up a synthetic division. Our coefficients are 1, -1, -14, and 24. And it means x equals -4 is our 0. Good. Yeah, so because we have x plus 4, we put it we solve that, we get x equals -4, and that's what number we put here in the box. Okay. Now, we know this is a factor because the problem told us so, and therefore we should get a remainder of 0 at the end. Okay. Alright, so we bring down our 1. We multiply. -4 times 1 is -4. Add. -1 plus -4 is -5. We multiply. -4 times -5 is 20. Add. -14 plus 20 is 6. Multiply. negative 4 times 6 is negative 24, and they add up to 0. And so we knew it should be 0, and it's nice to have that check that if we didn't get 0, that means we made a mistake somewhere. Now, we know x plus 4 is one factor, but what's our other factor now based on this? Or what's our other trinomial, first of all, before we go to a factorization? Yeah, x squared minus 5x plus 6. Okay, that means we need two numbers that multiply to 6 and add to negative 5. Which would be x minus 2 and x minus 3, right? Yeah, negative 2 times negative 3 is negative 6. Negative 2 plus negative 3 is negative 5. So yes, B is the solution. Okay. So that's one way I set up this problem on the test, where it can be 1, multiple choice, but 2, test a specific aspect of the problem, that of being able to check, is this a solution, verifying that it's a 0, and then factoring the remaining trinomial. Can we get the remaining trinomial and then factor it? So some very specific things I'm trying to test in this problem, but it leaves out the whole trial and error process of synthetic division, which I do enjoy shortening that aspect. So there will be one problem like this in the test, and that'll be one less problem where we have to go through and do all that extra work that we don't have to in this case. So okay. Let's look at, I want to look at 60, but I can see the answer next to it is not one of the early answers on synthetic division, so just to understand, it'll take a little while, unfortunately. We haven't looked at any where there's a number in front of the x cubed. Now, instead of giving us f of x, they've given us a polynomial equal to 0, but really our approach is not any different than what we did in the last couple of problems. So it shouldn't be an issue. All right. So we look at P. P is 5. We ignore the fact that it's negative. P is 5. Q is 2. And so we get 1 and 5 as our factors of P. 1 and 2 as our factors of Q. Both of these numbers are prime, so it's really just 1 in themselves that are the factors. Now, we actually get 4 different possible zeros, P over Q. Can anyone list those out? 1, 5, 1/2, and 5/2, right? Again, we take 1 over 1, 5 over 1, 1 over 2, 5 over 2. So each p is divided by each q. So we take each of these divided by the first q value, and each of these divided by the second q value. And if they had more terms, we would just continue as far as we needed to. But yeah, so we do have 4 different possible outcomes here. I will say, in this case, we are looking for a positive number just to shorten the process out. So I might, if this came up as a test question, I might give you a hint that 0 is positive. Depending on how the question is. Now, I'm probably not going to use a question like this where there's only one real answer and the other two are, well, one rational answer and the other two are irrational. But if I did, this is how I would set it up, to give you a hint. That way we can ignore the negative numbers and just focus on the positive numbers. Now, the fact that we have a 2 in front of the leading term rather than a 1, it means more than likely one of our solutions has a 2 on the denominator, 1/2 or 5/2. But, generally we'd still like to go through 1 and 5 first because those will be easier to check than the fractions. Okay, so we try x equals 1. Let's see, that would give us 2, -3, -3, -5. 2, 2, 1, -4, -4, and -9. So does 1 work? Well, no, because we didn't get a remainder of 0. So x equals 1 does not work. So let's try x equals 5. Bring down 2, and then 5 times 2 is 10. Add 7. 5 times 7 is 35. Add 32. 5 times 32 is 160. And then add 155. Well, we could tell once our numbers start getting bigger, there's no way if we keep multiplying by 5 that they get smaller, specifically small enough to become a 0 at any point. So, yeah, this one definitely does not work. We get a much larger number than 0 in this case. Okay, so what we've done so far is we've ruled out the 2 whole numbers, so it must be either 1/2 or 5/2. And again, we kind of suspect those because we have this 2 in front. Now, the deal is, it doesn't have to be that we find the 1/2 and the 5/2 first, because if there's a 2 in front, that means there's 3 solutions, 2 of which don't have a fraction. And so it might be that we happen across the one that doesn't have a fraction first, and we go from there, and we just factor it, or by quadratic formula, perhaps. Excuse me. So let's continue. And so we're still working with 2x cubed plus 3x squared. No, minus 3x squared minus 3x minus 5. And now we want to try x equals -1, or 1/2. Sorry. Yeah, we would try the negative numbers, but they actually don't work in this case. I was trying to keep us from doing 3 extra synthetic divisions that we didn't need to do. Basically is what that was. Ideally, just for our own sanity, it would be nice not to do more than like 3 or 4 synthetic divisions. Because even though they're pretty easy, it does get a little bit old. Especially with fractions, it's not nearly as fun. Now, the good thing about fractions, when we try to use them here, if there can be a good thing, is that if they work, they're going to be working very nicely, and if it fails, it's going to fail very spectacularly. Okay. Yes, if you like, you could do 0.5 instead. That definitely makes it easier to multiply on a calculator if you prefer. I'm so used to working with fractions. That's what I do. When I think about it in this terms, like what is half of 2? Because when you think of 1/2 times 2, it's not as intimidating as if we say, what is half of 2? Which is 1. Okay. I think that makes it a little bit easier, especially with the 1/2 term. Can't really do that with other fractions necessarily, but at least with the 1/2, we know we say half of 2 is 1. Let me add. When you think about what is half of -2, that would be a -1. We get -4. What is half of -4? -2. Add. Well, this actually worked pretty well. We didn't generate any additional fractions here. But we end up with -7, so it actually does not work. You know, x equals 1/2 does not work. Okay. So we try x equals 5/2. 5/2 is a little bit more tricky to use as a fraction. But again, the best way to think of that, I think, is saying we're multiplying by 5 and then dividing by 2. So we have a 2 down here. 5 times 2 is 10, divided by 2 is 5. Okay. But again, instead of writing 5 over 2, we could write 2.5 and just do the multiplication like that. We add, how about the 2? 5/2 times 2 is still 5. It's actually the same product we did here. Add, do another 2. 5/2 times 2 is 5 again. No surprise there, it's still the same product. But this time, it adds up to 0. Okay. So we finally got to a 0. So x equals 5/2 works. What are our factors now? X minus 5/2 or 2.5, and then 2x squared plus 2x plus 2. Good. Okay. Yeah, with these three 2's here, it's just 2x squared plus 2x plus 2 is the other part of our factorization. Now, this one turns out is not factorable. So, there is that. So we get x equals 5 halves. We know that's one solution. We already established that. But the other one, we have 2x squared plus 2x plus 2 equal to 0. We can factor out a 2. Actually, it might even be better just to divide out of 2, because we don't even need to keep track of it, really. When we're solving it equal to 0, we don't really have to keep track of the extra 2 that we have. But again, the issue is there's no combination of terms that multiply to 1 and also add up to 1. That'd be really weird. Anyway. Technically there is, but it turns out it's potentially imaginary, or at least irrational. So the only other way we can find our solutions here is by the quadratic formula, so we can utilize that. And so we'll say x is equal to negative b, negative 1, plus or minus, b squared is 1, minus 4, a is 1, and c is 1, over 2 times a, so 2. Under the radical, we end up with 1 minus 4, which is a negative 3. So our other two solutions are negative 1 plus or minus I squared 3 divided by 2. And it turns out to be an imaginary number. Okay. Now, more than likely, I won't put a problem like that on the test, where it has, I take that back. There will be a problem put on the test that has an imaginary pair of solutions like that, but that's actually from 5.7, not from 5.6, that we actually studied the complex solutions of polynomials. Technically, in this section, because we're only looking for real solutions, it only wrote down x equals 5 halves as a real solution, which is true, but we do have two other solutions that are not real. These are imaginary or complex numbers. Imaginary is just this number by itself. Complex is the whole thing. So. All right. Now, as far as what we cover in 5.7, there's actually nothing else, how to say this, it's, there's really no new material we need to cover. It's just, it'll be problems like this one that we just worked, where we get one real solution, and then we have to use the quadratic formula to get the other two solutions that turn out to be complex, or include imaginary terms, basically. So let me go ahead and work one of those examples, and then we'll be good. This will be on page 407, number 36. we're given f of x is x cubed plus 13x squared plus 57x plus 85. Now, there's one concept from section 6 that we actually skipped because it doesn't help us most of the time. However, this is one time where it does help us. And I think you'll be able to see the logic of this. We have this rule, it's called Descartes' rule of signs. It says the number of sign changes as we go from one term to the next indicates the number of positive solutions. And we look at this as positive, 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 positive. All four of these terms are positive. There's 0 sign changes, and that means there should be 0 positive solutions. So rather than introducing that as a topic, if we notice all of these terms are positive like we see here, there's no way we can take a positive number, plug it in, multiply and add all this together, and have it come out to be 0. So if we have a positive x cubed, a positive 13x squared, a positive 57x, and 85, all of these are positive numbers, and adding them together will still be positive if we plug in a positive number. How many times have I said positive in the last minute? Anyway. So, long story short, our answer has to be negative in order for this to actually equal 0. If we have a negative number, at least x cubed will be negative, and 57x will be negative, and then these will be positive. And it has a chance of equaling 0. So in this case, if all of our terms are positive, we can assume that our answer must be negative in order for this to somehow equal 0. Long story short. Another thing that we notice here, our numbers here are pretty big compared to what we've been looking at so far. 13, 57, 85. So that means it might be one of our bigger values that ends up being our 0 that we find. But again, it just depends. Now, even if we didn't notice that all the signs are positive and therefore no answer could be positive, even if we go through and test those, we'll just find that they don't equal 0, and really there's no harm there. Yeah, the only way to get 0 is to have positive and negative numbers cancel each other out. But if all the numbers are positive, there's no way to add up to a 0 because you don't have that balance anymore. Now we know 1 times 85 is a factor of, is a pair of factors for 85. Can you all think of the other pair? Five and 17, good. Probably the easiest way is to recognize 85, since it ends in a 5, it has to be a multiple of 5. And just do that division. 85 divided by 5 is 17. I don't know if that's what you did, August, but you may actually know 5 times 17 is 85. But yeah, there's two different approaches. Okay. So it's actually probably not 1, or negative 1, but we should try anyway. P over Q. Again, if we include all the positive answers, we know it's plus or minus, but realistically, it's not going to be positive. So we'll try negative 1 first. Even though we see our coefficients are so large, it's probably not negative 1 either. It might be 5 or 17. Unlikely that it's 85. If you do enough of these, then you start to to get a little bit better feel for it. And a lot of it, I think, is just having a good knowledge of how these numbers are combining together to create these zeros. Okay. 1, 12, negative 12, 45, negative 45, 40. Yeah. So negative 1 didn't work. That's not a huge surprise. Let's try x equals negative 5. So 1, negative 5, 8, negative 40, 17, negative 85, and remainder 0. Okay. So we get our remainder of 0. That means x equals negative 5 is a 0. And x plus 5 is a factor. The reason we know x plus 5 is a factor is if we set it equal to 0, we get x equals negative 5. So we're just reversing that process. F of x, we know one factor is x plus 5. Our other factor comes from what's next to our 0 on the synthetic division, 1, 8, and 17. So it'll be 1x squared, 8x, and 17 is the constant. And normally we would say, okay, we'll take 17. Can we find two factors of 17 to add up to 8? Well, the only two factors of 17 there are 1 and 17, and that adds up to 18, not 8. So that's out of the question. Generally what's going to happen is, yeah, 17 is a prime number. And because of that, unless that particular factorization works, then it's going to have to be a problem we solve with the quadratic formula instead. So negative b, negative 8, plus or minus b squared, 64, minus 4, a is 1, and c is 17. 2a is just 2 on the bottom. Okay. Now we look at what's under the radical. We have 64 minus, and then we have 4 times 1 times 17. Now 4 times 17 is actually 68. So 64 minus 68. That means we'll have square root negative 4 over 2. What is the square root of negative 4? (2i), good. So it's negative 8 plus or minus 2i, and it's divided by 2 on the bottom. Now the 2 just divides into both parts on top, so if we reduce these, what does that give us? Negative 4 plus or minus I. Oh, yeah, 2i divided by 2. Yeah. That'll be just an I, because 2 has to divide into both numbers. Don't forget that. It's all good. You know, we're just practicing it here. It's okay to mess up in practice. And that's what we learn from. Even if we mess up on the test, we're still learning from that. But ideally, we do better on the test than otherwise. So, all right. So that's all that we really want to cover there. Any questions on this? I'll actually make this a pretty similar problem where we find 1, 0, and it's actually this was not a terrible quadratic formula solving that we had to do, so I think something similar to that would be pretty nice. And then again, similarly reducible, so we just have a pair of terms there. Okay. Alright, so that means next time we do have a review. I'll make sure I upload that after class today. And then, so on Wednesday we'll review and then have a test on Monday. Or technically the test would be from Thursday until Wednesday next week. Just anything in that window, but if you want to take it during Monday's class, you could do that for sure. Does that sound good? I do want to give you a few of these to practice on. Not a whole lot, but just stuff I think that would help you get ready for the test. Because I think practice will be useful here. Let's see, 45 would be good. Gosh. 45, 49. That should be good right there. Just 3 for you to practice, and exactly. So on Wednesday we'll review, and on Monday we won't have class in order to allow time for the exam. Exactly. Yeah. Right. That way you can do the exam during that period if you like, or if you need to. If you don't have time outside of class, but otherwise we do have some flexibility as far as when we can take it, as usual. Yeah, so you all have a good rest of the day and practice these, and take care, and I'll see you Wednesday.